Hi, class. Today we're going to move on to part 4 of our series on the history of the atom. So we talked yesterday, we ended up talking about Niels Bohr, and his contribution to our understanding of the atom was to think of an atom as having a positively charged nucleus, small positively charged nucleus, like Rutherford showed us, but that there are electrons are orbiting that positively charged nucleus, much like planets orbit the sun, right? And he came to this by looking at the emission spectra and the absorption spectra of different elements. Now, how do we do that? We'll do a flame test on Thursday, and I'll show you some lamps on Thursday where we can see where we excite the atoms and they'll glow different colors. But what they saw was that a given atom always absorbed a certain energy of light and always emitted a certain energy of light. And we call that a spectra. Right? And Bohr was able to predict the spectra of a hydrogen atom very, very well using this simple model of electrons being like planets orbiting the nucleus. But it broke down in higher elements, heavier elements. I mean, we still saw the spectra in higher elements. We knew the idea of a spectra. We know the idea of the energy being absorbed or being released, the photon being absorbed, photon being released. We knew that was right, but something wasn't quite right with our model because it couldn't predict it for heavier, larger, more complicated atoms. So we kept looking. We said, well, so Bohr's on the right track. How do we extend that a little bit further? And people tried, and people tried, and people tried, and they couldn't figure it out. So where we came to is, since nobody could figure it out, maybe what we need to do is start all over again. Let's look at the same thing, but look at it in a different way. Right? Let's take those blinders off, if you will, and we'd be open to other possibilities. What else might explain what we're seeing? And at about this time, there were some other experiments that were showing that electrons sometimes were acting like a wave. Right? Sometimes they acted like a particle, sometimes they acted like a wave. So this was a really, really wild concept. And it kind of, people were like, no, you can't be both. How could it be both? And the answer was yes, it is a particle, but it's also a wave. So depending on how we interact with our electron, it'll act like a particle or it'll act like a wave. Right? So we can look at the same thing in two different ways, see two different things as we look at it. So yes, it's both. So if you look kind of at the little moving sign here I have in the bottom right of my screen, it says light is a particle, and then you kind of see it as it gets darker. We make the letters a little bit bigger. You see that that's kind of morphing into wave. So we can look at that little picture, and depending on how you look at it, it can be saying particle or it could be saying wave. And that's what we're seeing with our electrons. Depending on how we look at an electron, sometimes it's going to act like a particle and sometimes it's going to act like a wave. Major, major fundamental concept that is really kind of complicated to comprehend. But if we just accept it at face value, sometimes it looks like a particle, sometimes it looks like a wave. We don't need to get any deeper than that in a chemistry class. We can save that for physics. So this realization that sometimes it acted like a particle and sometimes it acted like a wave helped lead us to the idea of quantum mechanics. Now, Bohr kind of got us on the right idea that he could see that particles, the electrons, were at specific energy levels. Right? He had the different orbits, and it had to be in one of those orbits. But he didn't understand why. He just knew that it was there. And that kind of led us to the idea that the energy must be quantized or quantum, because not every energy was allowed, only certain ones. Only certain energies, only certain orbits were allowed. So the next gentleman we're going to talk about is Broglie, and he kind of took what Bohr was doing and he added on to it this idea that, well, what if we thought of the electron as being a wave instead of a particle? And so what he was thinking of is we still have this positive nucleus, just like Bohr was thinking, but instead of orbits, we're just surrounded by this negative energy that just kind of surrounds our nucleus. So we really just think of this positive nucleus. It's there, but this negative energy is surrounding that nucleus. So de Broglie took it one step further, and he said, well, what if we think of the electron as a wave, and that the different energies or the different orbits we saw corresponded to the electron making a complete wave. So that wave would completely fit. So if we just look at let's take this electron right now. I have it at the third level. I'm going to move it all the way down to our first level here. See if I did that okay. So our electron, it's just traveling in a circle around our atom. And you see that circle, it's kind of hard to see here, but you see a little dot that's kind of moving around that circle. And it fits. One wavelength of our wave fits on that circle. Now, if I move it a little bit off of the orbit, now watch here. It's not going to keep going in the same shape. And we see it's kind of shifting around. So here the wavelength doesn't match an orbit. This orbit's kind of in between the one wavelength orbit I started with. And if I keep moving this out, I can move it out a little farther, a little farther, a little farther. And then if I get it onto this, right onto this next energy level, we can see that at this point, it fits pretty well. So here's the second level of our orbit, second orbit, and it's allowing two wavelengths to fit around that orbit. And we can keep going. If we're in the middle of some orbits, the wave doesn't fit, it doesn't repeat. So de Broglie is saying that can't be a state that the electron can be in. It has to be in one of these where the orbit exactly matches an integer multiple of the wavelength. So I showed you the first one was a circle, that just had one. Then we had an oval, you can see it had two ends to it. Now we're at the third level, we kind of got like 3 bumps to it, and I can move it out to a fourth level, and we can see 4 bumps here as well. So that was the idea that kind of helped explain a little bit more how a wave ability of an electron fit in to our picture. And that still was a little bit hard to understand. And where we got with was Erwin Schrödinger. You might have heard of him. Schrödinger's cat is something he's famous for. But he went ahead and he took this idea, this wave idea that de Broglie helped to push to the forefront, and came up with a completely different math to explain what was going on. Completely different math. So I just want to show you a few quick slides from a lecture that Schrödinger gave at Georgia Tech when he was explaining this kind of math. And as you look at this, there's all sorts of weird math symbols on here. For those of you that do go on in your math, you'll see that this is calculus, and this is even a very specialized type of calculus. And it goes on, and he's going through and showing how well this math, and he's deriving all these different things. And it goes on, and he starts talking about these different shapes and keeps going and going and going and going. And it finally gets to the end where he basically says here that if you look in this box here on the left side of my screen, that the standing wave that de Broglie was thinking about has to be a requirement. The wavelength determines the energy. They're about in the middle of this box. And many different possible states can be occupied in the electron, each with different energies and different wavelengths. And that's kind of what de Broglie was saying. So if we look at this piece here in the middle, right, here's our energy level 1. It has 1 wavelength, or really kind of half a wavelength. And here it has 2, and here it has 3, and here it has 4. So like 1 bump, 2 bumps, 3 bumps, 4 bumps. And that gives us the energy levels. So that fits in kind of what de Broglie was talking about. But at the end of the day, when we look at what Schrödinger was telling us, is that no longer do we have exact orbits, because we really don't know where that electron is. Schrödinger's math comes up and it tells us we have a good idea where it is. We know a probability of where it is, but we don't really know where that electron is. So we can't have orbits anymore. We don't have orbits anymore. And we'll get to that here in a little bit here as I go a little bit deeper. Now, about the same time, Heisenberg was getting involved, and he came up with an incredibly important principle called the uncertainty principle. And this is a big underpinning to most of quantum mechanics. And his idea was that it was impossible to know both, big bold letters there, both the position and the momentum of an electron at the same time. We can know one, but not the, if we know the position, we don't know the momentum. If we know the momentum, we don't know the position. Right? So we're saying we can't know both. Seems really counterintuitive because in the world we live in, the macroscopic world, the big world, we do know those. But you get down into the atomic world, we do not know those. Right? So position, again, is where it is. We can talk to where it is on our number line, where it is in our map. Momentum is how fast you're going, what speed you're going, what direction you're going. Okay. So to kind of drive this point home, I want you to think of a picture of a car here. And as we look in the car, we can tell its position sort of, like, because you can look at the cones and you can see the back bumper of the car is kind of lined up with this row of cones on the right, and each wheel is aligned with a cone. So we can tell the exact position of this car. But what direction is this car going? What direction is this car going? Is it going forwards or backwards? Well, you really can't tell. It's just a picture. So we can't tell which direction it's going. Can we also tell? Can we tell how fast it's going? Well, we really can't even tell if it's moving just by looking at this picture. So we don't know the direction. We don't know how fast. That means we don't know the momentum. We know exactly where it is. We can say it's that the back wheel is lined up exactly with this particular cone. Right? So here's a picture. We know the position, but we don't know the momentum. We don't know the direction and the speed that it's moving. I could show a similar kind of a picture. Let's look at that same little car again. And now we show a picture of this car that kind of looks like this. Well, we're used to seeing, if we see a picture where there's something blurry, that tells us, we're used to thinking that the object's moving. Right? That's why it's blurry. Right? So can we tell the exact position of the car? Could we point to exactly where the middle of that back wheel is? Not really. We know it's somewhere in here, but we don't know exactly where it is. Do you know which direction it's going? Well, we can infer that since the car is on a highway, that it's going to be going forwards. Otherwise, it'd be really dangerous. So, yeah, we probably have a pretty good idea which direction it's going. It's going to the left as it's going down. Can we tell how fast it's going? Sort of. If I had some sort of grids on here, might be able to say, well, it looks like the back position of the wheel could be over here someplace, and the front position of the back wheel could be over here, and we know that it was somewhere in there, and here's the time frame. So we might be able to get an idea of speed by doing that. But the idea I want you to see here is we definitely do not know the position. We probably, pretty sure we can tell the direction's going to the left. And we can get an idea how fast it's going by kind of how blurry it is, how spread out that blur is. Okay, it's a little bit different than that first picture. So taking what Heisenberg was telling us, since we can't know both at the same time, all we can do is use probability. Where is that electron most likely located? Most likely located. Mind-blowing idea here. So that's going to take us on to the idea we don't have orbits anymore. We're going to come up with the concept of an orbital. And the idea of an orbital, yes, it's very similar to orbit. And I think that's probably related to the scientists were trying to say, hey, Bohr, you really did a good job. Orbits were a great way of thinking about how the atom works, but it's not quite right. Very similar, but not quite right. So instead of calling them orbits, we're going to come up with the idea of orbitals. And as I explain this, I want you to think about this for a moment. We're talking about, we know where the electron probably is. So if you were to bet, if you were going to place a bet, or if I asked you, if I would say, I'll bet you $100 if you can find a B. Well, where would you look for the B? Right? Would you would you look for it inside our classroom? Would you go out into the parking lot? Would you maybe go to where we have some of those vegetables right outside the back door of the school where there's lots of plants? Would you go to a beehive? Well, if you think of all those different places I mentioned, there's a different probability finding the bee in any of those places. Probably wouldn't find it in the classroom. Very, very rare. I've been in this classroom for 3 years. I haven't seen one yet. If you go into the parking lot, you might see one. but it'd be very rare to see one. You go into where some of the veggies are outside the door here. Yeah, there's a pretty decent probability you would find one, but you know, we're getting a little bit better. You go to a beehive, you're pretty positive you're going to find that bee. So this is what we're talking about when we're talking about probabilities. So I want you to think of an orbital being in that same kind of an idea. An orbital, we're going to call that a region of space where there's a high probability of finding that electron. So just like there's a high probability of finding a bee in or near a beehive, and there's a low probability of finding that bee inside my classroom, think of an orbital as just kind of defining that for the electron. Where are we most likely to find that electron? Okay. Now we further go on in quantum mechanics, and it tells us that in a given orbital, this given region, there can only be 0, 1, or 2 electrons in that orbital. And quantum mechanics explains that very nicely, why there can only be 0, 1, or 2 electrons in that orbital. Right? Never more than 2. Very key point. Never more than 2. Now, these orbitals have different sizes, different shapes, different names, and we'll talk about that a lot more tomorrow. That's going to be a whole topic in and of itself as we try to understand this next level deeper in our understanding of the atom. So be sure to come back to, we're going to have our live class because this is going to be a little bit more complicated. I want to make sure I'm actually with you and we can walk through this together. So please, please, please make every effort to attend the live class tomorrow. It'll be much easier to learn it with me tomorrow than to try to watch a class video or a recorded video of it. Give you an opportunity to ask questions. Please ask me questions. Also, don't forget to answer the lecture questions after today's video, and come back tomorrow, and we're going to take this to the next level. All right, class, have a good one. See you tomorrow. Bye.